Hi, thank you so much for joining me. In this video segment, we are going to be looking at some of the introductory terminology and background information to help support us as we delve into thermochemistry and thermodynamics. The first term that we want to know is what is a state function. A state function depends only on the initial and final state of a process. Whoops, that's an L. State. It is independent on the path. So back in the olden days, if you were home and you went to school, we would talk about the distance as the crow flies. In other words, that direct, all that matters was your beginning and your end. That would be a state function. Another function that is not a state function would be, say, the amount of gas that was expended. That would depend on whether you stopped at your friend's house and then went to Sonic and then maybe had to get some tiny donuts, and then you might have ended up at school. So that would be the difference. A state function depends only on the initial and final. A non-state function would depend on the pathway that you took. So we would often put a delta in front if it is a state function, and a delta in chemistry is final minus initial. Now, a chemistry example would be a solid going to a vapor. The energy that is involved is independent of the pathway. I could go from solid to liquid first and then liquid to vapor, or I could sublime and go directly from solid to vapor. Regardless of which pathway I took, the energy involved, the enthalpy, would be the same. That's a state function. Energy is the ability to do work. Now, work is going to be defined very specifically in chemistry as it is in physics. Work is a force working or acting over a distance. And that's really key here, is the concept of distance. So I can push and push and push and push on the wall all I want, but that wall's not going to move. And if the wall doesn't move, I've not done any work. I've expended energy, but that energy has not done work for me. So work is not a state function. Now, we do need some sign at terminology, and in this unit, it's honestly going to be signs, whether values are positive and negative, and units. Especially watch for joules versus kilojoules. That can be really problematic, so keep your eye on those. Now, work done by a system. So the system is that region of the universe that we are studying. We define our system. Directly around our system are our surroundings. So if the system does work on the surroundings, that work is going to be positive in value. If work is done by the surroundings on my system, it's going to be negative. Okay, so let's take a look at some examples. The only type of work that we're going to be doing in chemistry is called PV work, and we'll see that in just a minute. Let's get a couple more terms down. Heat is the transfer of energy between objects of differing kinetic energy. And if they have different kinetic energy, they are at a different temperature, since kinetic energy or temperature is a measure of the average kinetic energy. So heat lost from the system is negative. Heat gained by the system from the surroundings is positive. Now, our internal energy of the system, we're not going to talk a lot about that at this level, but you should know the basic definition, that it's going to equal the heat exchanged and the work involved. And all of this is going to be calculated under standard ambient temperature and pressure. Ambient is 25 degrees Celsius. Unlike the gas laws that you have likely already studied, standard there is 0 degrees Celsius. With thermodynamic variables, scientists that began all this research defined standard as 25 degrees Celsius. So sometimes it can be helpful to call that SATP for standard ambient temperature and pressure. Now, I briefly mentioned before, the only work we're going to be doing, calculations with work, would be with a gas, and we will look at changes in volume of that gas. So work in that case is minus the external pressure times the change in volume. So if I have an expansion, okay, my final volume is bigger than my initial volume, so the change in volume is positive. If the change in volume is positive, the work is negative. So that's going to be a system in which, a situation in which my system is doing work on the surroundings. Now, if the surroundings are doing the work, my change in volume is negative. So remember, delta V is going to be final minus initial. And if my final is a smaller value than my initial, I'm going to get a negative delta V. A negative delta V times the negative in the formula would mean that work would be positive. All right, so this is, I haven't seen these calculations on an AP Chem test lately, but you may see them in your Gem Chem class or on an IB test. So you want to make sure you practice these a little bit. So if I have a volume 1, so this is my initial volume, this is my final volume, and I have an external pressure of 3,000 pascals. I want to keep everything in SI units. So joules and meters cubed and pascals would be my SI, my System International units here. To contrast that, 1 liter is a decimeter cubed, 1 milliliter is a centimeter cubed. I'm doing this calculations in meter cubed, so I'll end up with joules. So my work is going to be equal to minus my external pressure, which is 3,000, times my final volume minus my initial volume. And that's going to give me minus 15,000 joules, or minus 15 kilojoules for my work there. Okay, thank you so much for joining me for this quick introduction. I really appreciate your time.